Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about circular motion, where complications can arise, where the particle may leave the circular path. Let's consider a mass of m kilograms hanging vertically on the end of a light, smooth, rigid rod of length r meters. The light, smooth, rigid rod means there are no complications from its weight and that it's guaranteed to stay in a circular path. If we set it in motion with an initial speed u meters per second, then it will certainly follow that circle, but what will happen next? Well, there's the initial configuration and the general position. It starts at A and we're considering it to have reached B. Now, in the process of the angle theta there shown increasing, what we'd expect is that the rod and the mass will slow down, and then we'd expect it to function as a pendulum, swinging back and forth. It could be that B will reach right up where I'm putting a mark now. It could be up as far as there and still swing back, which would be rather spectacular as a pendulum, but it would still be a pendulum. On the other hand, if U is large enough, it'll get beyond even where I've put that blue mark. It'll reach the top where I'm marking again, and it will pass beyond that and go around the other side, and then it'll make full revolutions. There will be a limiting case where it just reaches to the top where I've put my second blue mark, just gets to the top, let's call that point C for a moment, and just stays there, reaches zero speed and is just balanced. That may not be very practical, but in theory that could happen. So what values of U would generate these various scenarios? Well, let's begin by doing some analysis. There's our picture again. I've this time added in the speed v to the diagram. Let's analyze it from the point of view of energy. If we agree that the zero level for potential energy is at A, then the initial energy will just be kinetic, and it will be half mu squared. On the other hand, when it gets to B, there will certainly be kinetic energy with the changed velocity v, and in addition there'll be some potential energy, which will be mg times the height gained between A and B. So that's the distance I'm marking there. Now that will be the full r from O to A minus the adjacent triangle, the adjacent side of the right angle triangle, including theta. So that will work out to be r times 1 minus cos theta. So that's an equation relating uv and theta. We can immediately see that the m's will cancel, and it would look simpler if we multiplied everything by 2. So let's do that. So we'll get u squared is equal to v squared plus 2gr times 1 minus cos theta. Now that's our energy analysis, but it would still be simpler if we could say what v squared was in terms of the other, because u squared is going to be a given, and so are g and r. So if we say v squared equals u squared minus 2gr 1 minus cos theta, we can see that that tells us that we'd expect the speed to decrease, at least initially. We're taking something off u squared, and we'd also expect to find a situation where possibly v reaches 0, but we'll see what happens. So there's that analysis once again. So what are we going to do with that? Well, we need to ask ourselves what happens when theta is equal to pi. So let's do that. There's the expression. What happens when theta equals pi? Well, there cos theta is minus 1, so v squared will be equal to u squared minus 2gr times 2, which is minus 4gr. Well, now that shows us that in order to have a sensible model, we'd have to have u squared is greater than or equal to 4gr, otherwise we'd be predicting a value for v squared which is negative. So that leads us to the condition that for v squared to be strictly non-negative at the top, we'll have to have u squared is greater than or equal to 4GR. And that turns out to be the condition that we want. It's 4GR is the borderline between the cases where if it's smaller you get a pendulum, and if it's bigger it completes full revolutions. So there's the condition, and we can express it as saying that u is greater than or equal to the square root of 4GR. You may prefer to write that as 2 times the square root of just GR. That then is the minimum value of u to achieve a full circle for a particle on a light rod. Well, it could also be a particle in a smooth circular tube. The model would be just the same, and the condition would be just the same. On the other hand, other things could happen if the model is a situation a little bit different. What, for example, if we have the mass m kilograms hanging vertically on the end of a light inextensible string? Now, if we set that in motion with initial speed u meters per second, there are other possibilities. It'll follow a circular path to start with, but it could get so far and then the string goes slack and it fall out of the circle. So if u's small enough, it will oscillate just as before, but if u's large enough, it will be theoretically able to get to the top, but it may in fact be the case that the string becomes slack. Let's suppose it does that at a point which I'll label as C, in which case it would then come out of the circle and behave like a projectile. So we could study its motion and predict what would happen on the basis of its being a projectile. Now, what about the particle A placed on the top of a smooth, rigid cylinder? And that's supposed to be a vertical section of a smooth, rigid cylinder. What will happen if it's released? Well, in this case, we'll have a similar setup. We'd parameterize it in the same way. We'd expect the particle to follow a circular path, remaining in contact with the surface. But if it's sliding around the surface, you really can't expect it to get to the bottom of the circle down here. That would somehow mean it was attached to the drum, which doesn't make sense. Instead, we'd expect it to travel to a certain point where it would leave, let's say it's B, where it would leave the circle, and just as the string going slack, but in this case slightly different, and then it would travel as a projectile. So those two scenarios, the string going slack or the particle flying off a cylindrical drum, are the two that we'll study in the next two videos. So that brings this one to a halt, and the next is the particle on a string.